Okay, so video number 2 for Unit 5, focusing on designing and conducting an investigation to determine how potential difference, which is also known as voltage, you've probably heard of that before, and resistance affect current in an electric circuit. So we've got 3 new things here that are all interacting: potential difference, or voltage, resistance, and current. And we're going to be designing and conducting an investigation with this to meet the learning objectives. So certainly we're going to be doing a lab with this, and you're going to need to connect your results of your lab to that experiment and to this learning objective. I'm going to try to go through a lot of background information here that's going to help make more sense and have a deeper understanding of what's going on in the lab. And this is going to be a lot of information, so we're going to try to move through it quickly. Let's get started. First thing we need to review is the idea of action at a distance forces. And so there were 2 types of forces we talked about back in Unit 2. The first type was a contact force, where the 2 objects, in this case, this boxing glove and this face, actually come in contact to make the force. Now, along with the idea of contact forces, we also had the idea of action at a distance forces. Action at a distance forces are forces that exist even though the objects don't touch. So the moon and the earth pull on each other with gravity. Notice there's a force on both objects, according to Newton's third law, even though they don't touch. And the same is also true of charged particles. Positive and negative objects can pull on each other at a distance, even though they don't touch. So here we're going to talk about gravity and the electrostatic force. Sorry, I need to put the word force in there. These are both examples of action at a distance because they allow objects to push or pull on each other without being in direct contact. Now, we want to take a deeper dive into this idea of action at a distance, and we're going to connect it with the idea of energy, specifically energy that is being stored in fields. So action at a distance forces are possible because the objects are interacting with an invisible thing called a field. For example, in the case of gravity, objects are interacting with what's called the gravitational field. And in the case of electrostatics, they're interacting with the electromagnetic field. In the case of gravity, the farther apart 2 objects are, the more energy is stored in the field, in the gravitational field. Okay, that's a little bit hard to understand. Let's look at this example here. So we've got the Earth and the Moon. Notice that when they're close together, they have large force of gravity. And as they move apart, as we go this way, the force of gravity gets weaker. And so if we're thinking about the energy in the field, we need to think about what is happening as you pull these objects apart. Well, pulling them apart is kind of like stretching a spring. And over here, when the string is really stretched, that means there's a large amount of energy being stored between those objects. And so here's what we're going to write. We're going to make a big yellow arrow going from here back to there. And we're going to say that I'm going to say that over here there is less gravitational potential energy. We know this from our energy unit. Remember, energy is based on height. So if the moon is lower, it's going to have less potential energy. And then over here, we have more gravitational potential energy because the moon has been raised higher up, and so we've stored more energy in the gravitational field. If we look at this situation where we have opposite charges, they're attracted just like the moon and the earth are attracted. And so as we work to pull them apart, we're going to have less what's called electrical potential energy over here, and we're going to have more electrical potential energy over here. And so in this statement, the farther apart two opposite charges are, the more electrical potential energy is stored in the field. Specifically the electromagnetic field. But I'm just going to write field because it's shorter. If we look at this situation, it's actually the opposite. These charges are repelling each other. And so as they get farther apart, we're not pulling them apart. They're actually moving apart pretty much on their own. If we were going to apply energy, add energy to the system, we'd have to do it to push them together like that. And so it's actually the exact opposite. Over here, where they're far apart, they have less electrical potential energy. Whereas here, they have more stored electrical potential energy. And so the energy increases this way as you sort of, again, it increases because over on this side, we're essentially pushing them together and storing up energy, like we're squeezing a spring together. Whereas over here, we have more energy on this side because we've had to sort of pull the objects apart, storing energy. It's all about the fact that these ones want to attract, whereas these ones want to repel. Okay. So knowing that separating charges allows us to store energy allows us to start understanding what happens inside of the batteries that power all of our devices. The power of a battery is based on electric potential difference, which I'm actually going to highlight in purple here. Let's use the dark purple. Okay. So a battery is a device that uses a chemical reaction to move charges from an area of lower electrical potential to an area of higher electrical potential. So essentially, if you look at this example where you have opposite charges, the battery is moving charges from low energy to high energy. The battery is storing up energy. The difference in the electrical potential between the low and the high is measured in joules of electric potential energy, joules is our unit of energy, per coulomb of charge. So it would be written as J over C, which is joules per coulomb, but we usually abbreviate that as volts, capital V. So if we look at this battery, we have negative charges over here on the positive side, and they're being moved toward the negative side. So all these negatives over here, they want to escape. They don't like being together. They're trying to repel. And so there's a lot of electrical potential energy stored up in all those electrons right next to each other. We have like high electrical potential energy over here and low electrical potential energy over there. And so the difference, or the motion of those electrons, creates an electrical potential difference between the sides of the battery. And that electrical potential difference is written as 9 volts, 9 joules per coulomb of charge. Because it's measured in volts, we sometimes call that the voltage. The tool we use to measure voltage is called a multimeter. And I've drawn a picture of a multimeter right here as this little red box. Notice it says 9 volts. In order to measure electric potential difference, we need to compare an area of low electric potential to an area of high electric potential. And so the multimeter has 2 cables that come out of it, and those 2 cables have to touch the circuit, this is the electric circuit right here, in 2 different spots in order to compare the electric potential difference. So we're going to fill this in and say the measurement requires the 2 leads, is what they're called, leads of the multimeter, to be connected to different parts of the circuit so the voltage can be compared. If you were to touch the 2 leads to the same spot, it would always read 0 volts because there would be no difference. First thing we need to understand is the different parts of a circuit. So right here I have a circuit diagram. These lines indicate, like this line right here, indicate a wire. So between points A and B, there is a wire. This squiggle right here represents what's called a resistor. A resistor is any device that turns electrical energy into heat. The classic example we'll use in this class is a light bulb. This symbol with the 2 lines of different sizes represents battery, or any source of electric potential difference, any voltage source. Okay, so when we look at a graph of electric potential energy over here, we're measuring the voltage as we go through the circuit. So if you look at the graph over here, we've got point D and point A. So between point D and point A, there is a battery. So I'm going to go ahead and highlight this part of the graph in green, the same color as my battery. Then between point A and B, this part of the wire, between points A and B, I have just a wire. So I'm going to highlight it in that pink color. Between points B and C, I have a resistor, which I'm going to highlight in brown right here. And then between points C and D, I have a wire. And so what we're doing here, and what you're going to do in your lab, is we're comparing the electric potential energy at point D to the electric potential energy at point A, and we're seeing that there's this increase in electric potential energy over that part. There's a slight drop from A to B, and there's a big drop from B to C. So what we will see is that there is a rise in the electric potential across the battery, because the battery is providing the electric potential energy. There will be a slight drop in electric potential across the wire, and there will be a large drop in electric potential across whatever the device is. That could be a resistor, just generally. All right. The drop that we're seeing represents the amount of energy that is converted to heat in each part of the circuit. The voltage gain and the voltage drops in the resistors are always going to be equal due to the law of conservation of energy. What do I mean by that? Well, look over here. I've got a graph of the electric potential energy and the thermal energy from points D to point A. Well, you can see that this is the battery, and so there's going to be a lot of electric potential energy in the charges inside the circuit in the battery. And there's going to be no thermal energy that has been generated. as electrons then move out of the battery through the wire, they are losing electric potential energy, so that's going down. And where does that energy go? It becomes some amount of thermal energy. Wires do heat up slightly as electricity runs through them. Then in the resistor is creating an enormous amount of heat. And so there's a big drop in the electric potential energy and a big rise in the thermal energy. Over here, as we return back to the battery, we have now lost all of the electric potential energy, and that is all turned into thermal energy. So the rise, what we were saying is the rise in the battery has to equal the drops in the circuit, because the total energy never changes according to the law of conservation of energy. So this answers the question, why does my charger get hot? Essentially, the power from the wall into your charger is extremely high. It's very, very high voltage. But your phone can't receive that much voltage. And so the charger has to actually release some energy as heat as the electricity flows through into the phone. And that loss of energy is known as resistance. So as electrons, that shouldn't be red, there's no reason for that to be red, move through any conductor, that could be a wire or a resistor, they're going to lose energy in the form of heat. Smaller wires tend to have more resistance, because if you look at this little tiny wire right here, you can see it's hard for the electrons to move through there, whereas here it's easier for the electrons to move. So I'm just going to draw some red lines to represent the heat being generated. So here there's some heat coming off of this wire, whereas on this one there's going to be lots of heat being generated because it's a smaller wire. If you think about a toaster, what's happening is we're running electricity through these tiny little wires that have very high resistance. Oops. Have very high resistance. And so that is releasing heat. This is why toasters are actually super inefficient. They use a ton of electricity because they have to use up a lot of electricity in order to make all that heat. The amount of energy that is being lost is called the resistance of the wire or of the device. Devices with a large resistance are going to create a large drop in the voltage because they're taking up a lot of energy, compared to devices with a smaller resistance. So any device that converts this energy into heat is called a resistor because it has resistance. So let's quickly look at this electric potential energy graph. Again, here's the battery. Here are some wires. And there's actually two devices, two resistors in this. The question is, which one has more resistance? Is it the first one or the second one? We can answer that by looking at the electric potential energy drop in each one. This one has a larger drop in electric potential energy. This one has a smaller drop. And that's because this one, number one, is converting more energy into heat and has more resistance. This is a super interesting feature of electrical circuits, is that things that require more energy, like this resistor, automatically get more, which is really great because it means that you can plug in a hairdryer that uses a ton of energy into an outlet and it will receive all the energy it needs, and then you can plug something smaller and simpler like a LED light bulb or a phone into the same outlet, and it doesn't get overpowered and destroyed. It receives the smaller amount of energy that it needs. And even on a bigger scale, like when your neighbor is using a ton of electricity, they get all the electricity they need. And if you're only using a little bit, you get the energy you need and no more, which is really valuable, because if too much electricity is sent into your house, then it will usually cause things like electrical fires. And that's not good. All right, I know that was a long video, but there's a lot to learn about electricity, and this is just the basics. Good luck on that quiz.